Hello everyone, today I will be tackling a couple of number systems that can be used within your computer. Starting off, we will be taking a look at the binary number system. Binary number system is one of the most well-known one. It is a base 2 number system, and we will be taking a look at four uh, main parts or of the binary number system, sorry. Starting first, we have what is the binary number system. The binary number system is a type of numbering system that comprises one and zeros. It is possible to convert any decimal value into a binary number, which we will be taking a look at later on. Binary numbers are often used in computer system for computation within the CPU, as well as for lower level programming languages such as the hack programming language. As you can see here, I've given a couple of starter decimal value converted into 2 bits binary number. First, we have the number 1, which is 0, 1. The number 2, which is 1, 0. And the number 3, which is 1, 1. As for the number 4, you can see that I've listed it as question marks. This is because it is actually not possible to display the number 4 in 2 bits binary number. In order to display number 4 and henceforth, you need up to 3 bits. As you can see here, for our 3 bits binary number, we can actually display the number 4, which is 100, the number 5, which is 101, number 6, which is 110, number 7, which is 111. Now, knowing these couple of starting decimal value is important, but what's more important is knowing how to convert any decimal integer into a binary form, which we will be taking a look at right now. Decimal to binary conversion. There is two methods for converting decimal to binary. The first method we'll be looking at is division. In order to convert decimal into binary using division, we have to start out by dividing the given value with the number 2 while noting down the remainder. And then the second step is dividing the quotient received from the first division while also noting down the remainder again. And then you continue division until the final output is 0. Of course, also noting down the remainder from the final division. Finally, you reverse the remainder received in order to get the binary equivalent of the starting integer. Let's take a look at a few examples of this that out to help us tackle this method. I've chosen 3 different decimal value, 5, 12, and 36, starting with the value 5. First, we have 5 divided by 2, which is 2, with a remainder of 1. Now, we note down this remainder of 1, and then we take 2 to divide 2 again, we would get 1 with no remainder. Now we have the value of the output is 1, so we have to take 1 and divide it by 2 again. You can see we have a remainder of 1. Now, as you can see here, the quotient of 1 dividing by 2 is 0. Now we know that we have to stop the division, so we can put together the remainder that we've gotten from the divisions in order to get our binary value. So, which is 1, 0, 1 in reverse. Thus, the decimal integer is 5 is 101 in binary form. Moving on, let's take a look at the example number 12. First, we have 12 divided by 2 is 6 with no remainder, and then 6 divided by 2 is 3 with no remainder, and then 3 divided by 2 is 1 with a remainder of 1, and then we have 1 divided by 2 is 0 with a remainder of 1. Thus, the decimal integer 12 in binary form is 110. Of course, you have to reverse the remainder receives. Finally, with our final example, which is 36, we have 36 divided by 2, which is 18 with no remainder, and then 18 divided by 2 is 9 with no remainder again. 9 divided by 2 is 4 with the remainder of 1, and then we have 4 divided by 2, which is 2 with remainder 0, and then we have 2 divided by 2 is 1. Finally, 1 divided by 2, the quotient is 0 with the remainder 1. Thus, in reverse, the final The binary equivalent of the number 36 is 1000100. Moving on, let's take a look at the second method. This is my go-to method for smaller number, as you can uh, sorry, as it is quite easier to see. That is using a binary table. For this lesson here, we will be using an 8-bit binary system or value. Let's start with a couple of examples. We have the number 6. Uh, for the binary table method conversion, it is simply just taking a look at the given integer and then thinking of what is this actually made of. Let's say with the example that we have here, we know that 6 is made up of 4 plus 2. Thus, that is all that the value that will be used in the its binary equivalent. We will not be using the number 126, 64, 32, or 16. We won't be using 8 as it is bigger than 6. We know that 6 is made up of 4 plus 2, so 4 and 2 is used. 1 won't be used as well. It is actually that simple to convert from decimal to binary using this binary table. Although for a bigger integer, it might be a bit difficult. But moving on, I've also given another example of 14. Now, what is 14 actually made up of? We know that from 128 to 16 it's not possible to use this value because it is bigger than the given integer. So we know that all of the binary value from the first 4 is 0, starting from the left. Now, for number 8, we know that 14 is made up of 8 plus 4 plus 2. Thus, 8, 4, and 2 has the value of 1 since it is being used. Finally, 1 is 0 since we're not using it to add to the value of 14. Again, the takeaway from this is that in order to get the binary equivalent of the given integer, you just have to come up with the addition. What number are added together in order to come up with that value? The next example we have is 59. Now we know that 128 and 64 is bigger than 59, so those two obviously won't be used. As for 32, it is against use. You just need to come up with which value is needed to add to 59. So we have 32 plus 16, plus 8, we won't be using 4, plus 2, and plus 1. The next example we have is 111. Now, this one gets a bit tricky. The only value that we know won't be used is 128, 64 is used, 32 is used, 16 is not used, 8 is used, 4 is used, 2 is used, and 1 is used. So the binary equivalent of 111 is 0, 1, 1, 0, 1, 1, 1, 1. Finally, the next example is 120. 120 again is smaller than 128, so it obviously won't be used. 64 is used, 32 is used, 16 is used, 8 is used, 4 is used, 4 isn't used, 2 isn't used, and 1 isn't used. Thus, the binary equivalent of 120 is 0, 1, 1, 1, 1, 0, 0, 0. As for the last example, we have 255, which is actually made up of all 8 bits. So its binary equivalent is 1, 1, 1, 1, 1, 1, 1. Now, what happens if the value exceeds 255, or let's say the value is 256? 256 actually won't be possible to display in an 8-bits binary value. You would need a bigger bits one, which is what we'll be looking at in the next slide, which is actually n bits binary number. From the previous example just now, we already know that with an 8-bit binary value, the highest number that can be displayed is 255. Let's say n is the number of bits of a binary value. The highest number that can be displayed in a binary system is 2 to the power of n minus 1. Let's take a look at some example to help us understand this formula. Let's take, for example, 4 bits. We would have 2 to the power of 4, so 2 times 2, which is 4. 4 times 2 is 8. 8 times 2 is 16 minus 1, which is 15. This means that the highest decimal number that can be displayed in a 14 bits binary value is 15. A number from 16 and beyond, you will need a bigger bits binary. As for 5 bits, we have again 16 times 2 is 32 minus 1 is 31. So the maximum decimal integer that can be displayed in a 5 bits binary is 31. As for 6 bit, you would have 32 times 2, which is 64 minus 1, 63. 7 bit, you have 64 times 2, 128 minus 1 is 127. 27. Lastly, for the 8 bits we just looked at just now, we have 128 times 2, which is 256 minus 1 is 255. In our case, the most important n bits binary number we'll be looking at is the 16 bits binary, since that is the bits binary that is used by the CPU to handle different instruction for the computer to perform. In our case, the biggest decimal integer that can be displayed in the 16-bit binary value is 65535. Now let's take a look at some number displayed in a 16-bit binary value. This is again similar to what we looked at earlier in terms of how we can actually get this number in binary. Starting out with 86, we know it is only used. We only need to use 64, 16, 4, and 2. Adding these values together, we would get 86. We can still display this number in 16 bits binary value, even though we don't need to. We still can, just most of the value will be 0. Moving on, we have 159, which is made up of 128, 16, 8, 4, 2, and 1. Thus, its 16-bit binary equivalent is 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 1. As for 1250, we use 1024, 128, 64, 32, 32, and 2. Thus, its binary equivalent is 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0. Now, for bigger integers, you can still use the table to come up with your value, although it does get a bit messy trying to, do some like just doing addition to try and get those value. So I would recommend for big values such as 10,000 that you would just use the division method to come up with your 16-bit binary value. So as you can see here in the table, we have 0, 0, 1, 0, 0, 1, 1, 1, 0, 0, 0, 1, 0, 0, 0, 0. Let's do some division to see that if this number displayed up here is actually correct. First, we have 10,000 divided by 2 is 5,000, the remainder being 0. 5,000 divided by 2 is 2,500, with the remainder being 0. 2,500 divided by 2 is 1,250. Again, no remainder. 1,250 divided by 0 is 625 with no remainder again. Matching up so far. 265 divided by 2 is 312 with a remainder of 1. As you can see, 1, which means 16, the value 16 and the binary bits is used. And then 312 divided by 2 is 156 with the remainder 0. 156 divided by 2 is 78 with no remainder. 78 divided by 2 is 39 with no remainder. 39 divided by 2 is 19 with a remainder of 1. 19 divided by 2 is 9 with a remainder of 1 as well. And then we have 9 divided by 2, which is 4 with a remainder of 1. And then 4 divided by 2 is 2, no remainder. 2 divided by 2 is 1. 1 divided by 2 is 0 with the remainder of 1. As you can see here, we've only taken up 15 bits from this division, thus, 14, thus the final output will of course be 0. We have 0, 0, 1, 1, 3 ones, 3 0, 1 ones, and 4 0, which match perfectly with our table above. Let's do the same for the final example, which is 32, 56, 8. And to 16-bit binary, we have 325, 68 divided by 2 is 16, 284 with no remainder. 16284 divided by 2 is 8142 with no remainder. 8142 divided by 2 is 4071 with no remainder as well. 4071 divided by 2 is 2035 with one remainder. 2035 divided by 2 is 1017 with again one remainder of 1. 1017 divided by 2 is 508 with a remainder of 1. Sorry, 1017 divided by 2 is 508 with the remainder of 1. 508 divided by 2 is 254 with no remainder. 254 divided by 2 is 127 with no remainder. 127 divided by 2 is 63 with a remainder of 1. 63 divided by 2 is 31 with a remainder of 1. And then we have 31 divided by 2 is 15 with the remainder of 1. 15 divided by 2 is 7 with the remainder of 1. 7 divided by 2 is 3 with a remainder of 1 again. 3 divided by 2 is 1 with a remainder of 1. 1 divided by 2 is 0 with a remainder of 1. Thus, the final output is 0, 1, 1, 1, 1, 1, 1, 1, 1, double 0, triple ones, and triple 0, which match perfectly with our table above. Moving on, let's take a look at 2's complement in binary. 2's complement in binary is used to convert negative decimal into binary. So how do we do that? So in order to convert negative decimal into binary, we first have to compute the positive decimal value in binary first, and then reversing that binary value of the positive number, and then doing some addition by adding 1 to the binary value of the reverse binary value, and then that final output is the negative decimal in binary. Let's take a look at some example I've prepared. First, we have negative 5. Negative, well, 5 in binary 8 bits is 0, 0, 0, 0, 0, 1, 0, 1. And then we have to do the reversion, which is 1, 1, 1, 1, 1, 0, 1, 0. And then we add 1 to that value, we would get 0 plus 1, obviously would be 1. So the final output would be 1, 1, 1, 1, 1, 0, 1, 1. Thus, negative 5 in binary 8 bits is 1, 1, 1, 1, 1, 0, 1, 1. Let's move on to negative 12. Negative 12 in 8 bit is 0, 0, 0, 0, 1, 1, 0, 0. Reversing that value, we would get 4 ones, double 0, and double 1. Now, let's do some addition. We add 1 to the reverse value. We would have 1 plus 1. 1 plus 1 would normally be 2 in our usual cases, but 2 in binary is actually 10. So what happens here, you would place 0 into the bottom of the output area, and then you add 1 to the top of the next integer or the next bit. 1 plus 1 again, you would have 0 again. So 0 will be passed down to the output, and then adding another 1. 1 plus 0 is 1, and the rest is just moved down, so there's nothing to be added. Thus, the final value of negative 12 in binary is 4 ones, 0, 1, double 0. Finally, for our last example, we have negative 36. 36 in binary is 0, double 0, 1, double 0, 1, double 0. Reverse the value, we would get double 1, 0, double 1, 0, double 1. Doing some addition, we would have 1 plus 1. Again, we have 0, and then adding 1 to the top. 1 plus 1 again is 2, 0, adding 1 to the top. 1 plus 0 is 1. The rest is just moved down, so there's nothing to be added. Thus, the final value, that is a mistake, but the final value of negative 36 in binary is 1, 1, 1, 1, 0, 1, 1, 1, 1, 0, 1, 0, 0. Moving on, we will be taking a look at the hexadecimal number system. Now, what is hexadecimal number system? The hexadecimal number system is a base 16 number system that represents value from 0 to 15. But more importantly, how does hexadecimal play into computer system? We know that it can be used for HTML and CSS color coding. It can also be, which is for responsive web application. It can also be used for MAC addresses, which is for cybersecurity. But what we want to focus on here, which is why it relates to our unit, is the fact that it can be used in assembly language and machine code. It is often used to refer to the memory addresses and also to represent values stored in the CPU. As mentioned before, the hexadecimal number system is a base 16 number system. It can represent value from 0 to 15. So you can see down at the bottom, we have these values here, which is 0 to 15 in decimal. 0, sorry, the hexadecimal equivalent is listed down below. 0 is 0, 1 is 1, 2 is 2, 3 is 3, 4, 4 until up to 9. We have 10, which is listed down as A. 11 is B. 12 is C. 13 is D, 14 is E, 15 is F. These are the 16 default value for hexadecimal. Another thing I wanted to note is the fact that sometimes hexadecimal is actually preferred over binary just because it is actually shorter and faster than your binary value. Now, let's take a look at how you can convert decimal into hexadecimal. Conversion from decimal to hexadecimal is actually quite similar to how you would convert decimal into binary. You start out by dividing the given integer with the number 16, noting down the remainder, and then dividing that quotient received while noting down the remainder once again. Division will continue until the final output is 0, of course, noting down the division, the remainder once more. Finally, you want to convert the remainder received into hexadecimal and then reverse it to get the final output. Now, let us actually take a look at some example of how to convert decimal into hexadecimal to help us better understand this method. On the top, you will see I've listed out the remainder, the default 16 values, and then I've given us 3 examples here. First, we have 28. 28 divided by 16 is 1, with a remainder of 12, which is equaling to C. As you can see above, 12 is C. And then we have 1 divided by 16, which is obviously 0. Thus, division will be stopped here, with a remainder of 1 equaling to 1. We, we, we've already converted these two remainder already, which is 1 is 1, 12 is C. Now we have to reverse it to get the hexadecimal equivalent of 28, thus, which is 1C. Moving on, we have 102. 102 divided by 16 is 6, with a remainder of 6. 6 divided by 16 is 0, with a remainder of 6 again. Thus, the final value of 122 in hexadecimal is 66. Lastly, we have 1128. 1128 divided by 16 is 70, with a remainder of 8. 70 divided by 16 is 4, with a remainder of 6. 4 divided by 16 is obviously 0, with a remainder of 4. Thus, this value converted to hexadecimal is the same as its original value. Thus, the final value of 1128 in hexadecimal is 468. That is all we will be covering in this video. Thank you to everyone for watching, and I hope you have a good one.